Lecture 6. Lecture 6. Application of the Nabla operator in the non-conservative form. Okay. Now, the lecture 6 will apply to divergence of a vector. Attention now. Divergence of a vector is a scalar. Okay. Just so let's consider, okay, VM, AM, they belong to the space vector. Okay. Let's apply the Nabla operator. Okay. So divergence of V, recall that vector V is invariant. So in this case, Nabla dot V is a scalar which is invariant. Okay. So I'm representing this vector here on the space vector. That's it. So let's apply. Okay, I just repeat. You see, this operator right over here. Dot. Don't forget the dot. Now VM AM. Okay. Now we can expand this partial derivative here. Okay. We have two terms. Okay. AI dot. Don't forget the dot. Partial VM Xi AM. Okay. Now AM is covariant. VM is contravariant. Both belong to the space vector. Plus AI dot VM. This is a partial derivative here of the basis vector. Okay. Now attention now. AI dot AM is delta IM. And recall that partial of AM respect to Ci is the Christoffel symbols of second kind. Okay, we did this before. Okay, that's easy. No problem. Okay, so this over here. Okay, you can see this is a scalar quantity. Delta IM applied and VM Xi, you choose. You see partial VI with respect to Xi, or partial of VM with respect to XM. Doesn't matter. Okay, because they are dummy. Okay, scalar dummy. Likewise, the right hand side, the other term, okay, you just repeat from here to here. Again, you see here, I, okay? This I here is contravariant. This I here is covariant because this I here is in the denominator. So I just repeat I here and I here. Look how easy. M is dummy index. I is also dummy. Okay? So this relation is a scalar. Now you can compare this, see part 7, lecture 2. Okay? Then that's it. So the divergence of a vector. Now this A1, okay? The same vector V now will be expressed, okay, on VM AM. Attention now. VM AM belongs to the dual space vector or covector, as you said before. So let's apply here. See this operator here, Nabla. Okay, right over here. Dot VMAM. Now I'm going to expand this derivative over here. Okay, we have again two terms. Just look at AI dot AM partial VM respect to XI plus VM AI dot, you see, don't forget that, AM XI. Recall that this partial derivative here will be minus the Stoffel symbol, as we did before, okay? So there is no news here, you see? So then I substitute right there this partial derivative here, okay? So I just substitute this on there. Then divergence of I, attention now, AI contravariant dot AM contravariant by definition is a metric, is the contravariant metric, okay, which is GIM. You see, this is GIM. Now, recall that here is delta IM. It's different from there. See, delta IM here. But here is GIM. Now I repeat, GIM. So, no problem here, okay? This is AI dot, I just substitute, I get right here. I substitute this on there. Now attention now, GIM. Why GIM? There's a dot product of contravariant basis vector, okay? That I'm repeating in a substitute. Then I have VM, GIP, gamma IPM. No problem. Why? Why? You see clearly that VM, AM, okay? They are dummy. So AI contravariant CI is also dummy. So I can substitute by any letters, okay? What I did over here. So G, IP, gamma, M, IP. Look how interesting. You see, that's very clear here. You see? So P is dummy, I is dummy, M is dummy. So again, divergence of vector V, okay, is a scalar quantity, okay? Now I can write, see, I substitute P by M, just this to be equal to that, and substitute P, no problem, and M also. So this leads to this relationship here. Multiply by, attention now, this is the contravariant components of the metric tensor, okay? That's it. So, that's for you. I think I already did this previously. Another point I'd like to emphasize, I changed, okay, the numbers over here, okay? It's lecture 1A, 1B, lecture 2, lecture 3, 4, 5, and 6, okay? So follow in the link, okay? That's it.